So in this section, we're going to talk about an application of matrices, and it's going to be encoding and decoding messages. So we're talking about cryptography here and coding theory. So keep in mind, we are doing this on a very small level. So we're going to be using 2x2 and 3x3 matrices. But the general idea is really the same as if we were taking this to the national security level, where they're going to use a much larger matrix to encode and decode messages. So before we talk about encoding messages, we need to talk about what modular arithmetic is. So modular arithmetic is sometimes called clock arithmetic. And this is something that you've seen before. You just didn't call it what it was. Think about military time. So if we're talking about military time, so military time is based on 24 hours. So if someone told you it was 13 o'clock, what time would that be? Well, we know that that would be equivalent to 1 o'clock. So how did we get that 1 o'clock? Well, if you think about your clock, here's our clock. You would just kind of go around and you would just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 13 would put us right back here. So it's called clock arithmetic because we can just kind of keep going around and around and around the circle. So then 15 o'clock, we would just keep going. If we're at 12 here, 13, 14, 15 would put us here at 3 o'clock. So you can see why it's called clock arithmetic. Now another way to think about this is in terms of mods and division and remainders. This is actually the remainder if we were to divide by 12. We would call clock arithmetic mod 12 because time is based on the 12-hour interval, and then we start over again with 1 o'clock, 2 o'clock, 3 o'clock. Once we get to 12, we start over at 1, 2, 3, and so on. So we can think about this in terms of modular arithmetic. If we were to take the number 13 and we were to divide it by 12, well, 12 goes into 13 one time, and the remainder is 1. Whatever the remainder is what your answer would be here. Same thing with the 15. If we divide by 12, 12 goes into 15 one time, and the remainder is 2. Just kidding, the remainder is 3. So then 15 o'clock would be the same thing as 3 o'clock. So we're going to end up using that remainder idea when we think about modular arithmetic. And that works great for positive numbers. So let's talk about how this is going to work. Let's look at a different one. Let's say we're looking at mod 5. So if we're talking about mod 5, we're talking about the numbers. It's got to have 5 numbers in it. And for modular arithmetic, we always start at 0. So we're going to have 0, 1, 2, 3, and 4. Okay, notice that gives us 5 numbers in this set. So if we're talking about the number 12 and we want to be under mod 5, then that's going to be equivalent to the remainder. So what is that remainder? Well, that remainder, if we were to divide 12 by 5, it goes 2 times, and the remainder is 2. So we're looking at that remainder of 2. What if we were looking at 21 mod 5? Well, that same kind of process holds. We're going to take 21, we're going to divide it by 5. 21 divided by 5 is 4. but the remainder is 1. So 21 mod 5 is equivalent to 1. So you can kind of get the idea how this is working. Now, what about negative numbers? With negative numbers, what we want to do is we want to add the modulus until we get to a number that's in our set. So if we're talking about mod 5, and a lot of times the notation is going to be that funny z with that 5. That tells you the modulus. Remember, that tells you how many items have to be in the set. We always start at 0. So if we're thinking about the number negative 2, here's our clock. So the number negative 2 is actually the number 3 if we were to go back. So another way we can think about this is we just add the modulus to it until we get to that number. Or we can use that clock and we can go backwards. Let's do another one. What if we have negative 7 under mod 5? Well, if we're looking at negative 7 under mod 5, thinking about this clock again, we're going to go backwards 7 times. So 1, 2, 3, 4, 5, 6, 7. So we're going to end up at that 3 using the clock. Another way to think about this is we just add 5 until we get to a number that's inside of that set. So negative 7 plus 5 is a negative 2. And if I add 5 again, I'm going to get a positive 3. So there's 2 ways to think about it, in terms of the clock or in terms of adding and subtracting. So when we talk about encoding and decoding messages, everything's based around some kind of modulus. Now, for us, we're going to keep it simple, and we're going to look at just mod 26. Now, why would I look at mod 26? Well, we have 26 letters in our alphabet, so we can just keep it simple and just look at how many letters I have. Now, if we were doing this for national security purposes, we would want this to be a little bit more complicated. So we could include things like periods or commas, or we could include a blank space. So instead of having 26 items in their set, we would have 27, 28, 29. So you can see how adding more numbers means a more complicated modulus. But let's keep it simple. We're just going to kind of run our words together, no spaces in between, just to get our feet wet on this. So messages can be encoded using matrix multiplication. And we're going to use the following method. So our encoded message, and this is going to be in numbers, is going to be equal to the encoding matrix times the message in number form. So if we want to encode math, then we would say math is equal to 12, 0, 19, and 7. So let's do that. Now, for this to work, you have to have an encoding matrix that's going to have a nice inverse. And the inverse is not going to be under the modulus. It's just going to be a regular inverse. So let's look at this guy. I'm going to use this as matrix A. So our inverse matrix is going to be a nice matrix. It's not going to have any fractions. We can't have fractions and have this work out. Not with the method we're using. So our inverse, I'll do some scrap work over here. It's going to be 1 over AD minus BC. So that's going to be 1 over 1. So it's going to be 3, negative 1, negative 2, 1. So let's say we want to encode the message math. I have to choose something that's where that matrix multiplication is gonna be defined. So if I'm using the encoding matrix, that's a 2 by 2. Then for this multiplication to be defined, this has to be a 2 by something. And that something's going to depend on how big the message is. We're using a 4-letter word, math, so we're just going to use a 2 by 2 here. So our encoded message will be our encoding matrix times our message in word and letters. So we said M was 12, A was 0, T was 19, and H was 7. So when we multiply this together, we're going to get that. So there's our encoded message in numbers. But notice that some of these numbers are outside of that table that we're using over here. This is where the modular arithmetic is going to come in. So we're going to convert this using our mod 26. So if we take 31 and we divide by 26, it's going to go one time and our remainder is going to be 5. So we're going to have a 5 there. 7's okay because it's in that table. If we take 81 and we divide by 26, 81 divided by 26 goes 3 times. And the remainder is 3. So 3 is going to go here. It's always the remainder. And then 21's in our table also. So now we're going to go back to that table and we're going to say, we need a 5. Well, 5 was the letter F. 7 was the letter H. 3 was the letter D. And then 21 was V. So then your encoded message would be FHDV. So think about if you were encoding this to someone and you sent them that, they would have no clue what that means. But if it got to the person who knew what the encoding matrix was, then they would be able to decipher the message. So there's our encoded message. Now let's talk about decoding. If we want to decode, then we're going to have to take the inverse of the encoding matrix times that encoded message that's in numbers. So let's say, now let's pretend we don't know what this is equal to. But we knew the encoding matrix. So our encoding matrix was 1, 1, 2, 3. We need the inverse of that times FHDV. So we know what the inverse of this matrix is. We found that to be 3, -1, -2, 1. F is number 5, H is 7, D is 3, V is 21. So if we were to multiply those two together, then we're going to end up with 12, 0, -7, and 7. So now we just have to figure out, what is this equivalent to? So if we take -7 and we add 26, we're going to get to 21. So now we have all of our numbers. Let's figure out what our matrix says. So 12 is M, 0 is A, 19 is T, and 7 is H. So you can see how that spells M-A-T-H. So that's kind of cool, huh? How we can encode and decode. Let's do another one. Let's do one with a 3x3. Let's say we have our encoding matrix. And we want to encode the message. This is fun. We really should do this is awesome. But we'll keep it a little bit simpler and we'll do this is fun. Because this is totally awesome. So our first step is we need to turn this into a matrix. So I'm going to write it this way. So this is where you may want to pause the video and convert this. Try this yourself. And then come back and check. So now we have this is fun, written in numbers. So if we take our encoding matrix, 1, 2, 3, 0, 1, 4, 5, 6, 0, and we multiply it by our message, we're going to get a product. So our product, I got 70, 83, 83, 38, 88, 70, 203, 83, and 148. Now, for every single number, we need to apply the modulus. So we need to go with mod 26. Again, there's 26 letters in our table. We're keeping it simple. We need the remainder. So if we take 70 and divide it by 26, it goes 2 times, but we need to know what the remainder is. Well, that remainder is going to be 18. Same thing with 83. 83 divided by 26 goes 3 times. The mod is going to be 5. Take a minute, finish all of them. So we're going to get that. And now we need to turn it back into letters. So our encoded message is the nonsense that. So think about if you're on the receiving end of that. If you're on the receiving end of that and you get that, you're going to have no idea what that means. So there's how you encode. And we could go through the process and we could check the decoding. Let's do one where we have to decode. Let's do an example. So we want to decode the message OASVSKMOIJ using the encoding matrix of 1123. So let's look at this. So our first step is to figure out how we're going to write this. So we have a 2 by 2, and if we were to write this out, to make this defined, this guy has to be a 2 by 5. Okay, you know the inside dimensions have to match, so you just have to figure out what does this have to be for that multiplication to be defined. So that's how it has to be written. Now, let's put that into numbers. Going back to our table. Zero is 14. A is 0. S is 18. V is 21. S is 18. K is 10. M is 12. O is 14. I is 8. J is 9. So to decode, it's going to be equal to the inverse of the encoding matrix times that message. And I'm going to use the calculator to do the matrix multiplication for me. So when I multiply, I get this. Which is cool, except we need to apply modular arithmetic. So we're going to mod 26 every number. So we're going to have 6 here, 14, 14, 3, 19, 8, 12, 4, 18, 25. And then using our chart, let's see what this guy says. So this says good times. So notice there's a Z on the end here. So the message good times doesn't have enough letters to fill up that 2x5 matrix. So usually what happens is if you don't have a space in your table of values, which will change your modulus, by the way, then you have to fill in with something. So you usually fill in with some letter, like Z or A, or it doesn't really matter what letter you use. So that's what this guy is. It's just a filler. So now we could totally change this if we wanted to. We could add a blank in here. So we would have just a blank space. But then, like we said before, that would change this to mod 26, mod 27, because we now have 27 different entries in here. So we're going to keep it simple. So let's just do one more just so we can kind of demonstrate that. Let's encode the message. And we're going to do Math Rocks. So we have non-letters. And let's say we wanted to force a 2x2. So let's do the encoding matrix. How's that? 1, 1, 2, 3 again. So since we have non-letters, to make this multiplication defined, we would have to have a 2x5 here because we need 10 entries to get all 9 in. So MATHROCKS. But you gotta have something to put in here. You can't just leave it blank. And our table doesn't have a space for a blank number in there because we're still operating under that mod 26. So this is where you're going to want to fill in with some kind of filler. And it doesn't matter what you use. You could use Z, you could use A. You can use anything you wanted to. So this is where you may want to pause the video and encode and see what you get. And then compare with the end. I'm going to use the calculator to multiply. Then we need to apply our modulus. So 26 under mod 26 is 0. 29 under mod 26 is 3. 42 under mod 26 is 16. 66 under mod 26 is 14. 68 under mod 26 is 16. 109 under mod 26 is 5. So this is the message A, C, D, Z, Q, Z, O, not 0, O, G, Q, Q, and F. So there's our encoded message. So there's lots of different ciphers out there. We could spend days talking about ciphers, but this is one way to encode and decode messages. It's similar to the way that encoding and decoding is actually used at places like NSA. But like I said, they're not going to use like a 2x2 or a 3x3 matrix. They're going to use something quite a bit bigger, and their algorithms are going to get a little bit more interesting as they go through, because they really don't want those things to be cracked. This is one of my favorite part of linear algebra, where we can talk about encoding and decoding things. It's just fun.